Good afternoon. Welcome to SCA's webinar with Dr. Bob Merrill on visual cuttings and core description to characterize reservoir and non-reservoir rock. Before we start today's webinar, we'd like to ask a few questions of our audience to learn about our demographics. And so I'm going to share some polling questions. And the first question is, what is your primary discipline? And so we have several choices. I would expect we'd have a significant number of geoscientists, but it looks like we also have some petroleum engineers and some petrophysicists in the crowd. Most of you have voted, so I will go ahead and close that poll and share the results. Looks like we had 82% geoscientists and the rest distributed between petroleum engineers and petrophysicists. So our next poll is how many years of full-time experience do you have? Again, we have a variety of choices, and I've launched that poll. We're starting to get some answers now. Looks like we have a pretty good distribution among the various choices. Quite a few in the 1 to 10 year area. That's the largest. I'll go ahead and close that poll and share the results. It looks like 36% of you have 1 to 10 years of experience, and then there's a bimodal distribution. 27% have 11 to 20 years, and 27% have over 30 years. And so I'd like to go ahead and introduce our speaker today. And of course, this is part of our webinar series that we've been running to introduce instructors. Dr. Bob Merrill will be speaking, and he has quite a bit of experience in various parts of the world. Bob teaches a class for us called Visual Rock Characterization, and we'll talk more about this class, but it's generally available in-house. And as you know, SCA, in addition to training, we provide consulting and projects and studies and direct hire services. So without further ado, I'm going to turn the presentation rights over to Bob. And I'll remind all our participants that you are muted today, and so I will be reading your questions at the end of the presentation, and you will have a chance to pose questions throughout the presentation, but we will collect them at the end. So Bob, I think we're waiting to see your screen.
You should be seeing, let's see.
All right.
My screen isn't coming up all of a sudden.
Okay. I'm going to hide the polling results. Let's see if that helps.
Can you see the screen now?
Yes.
Okay. We're all set.
Take it away.
Thank you very much, Susan. This afternoon, I want to talk a little bit about visual rock characterization. It's something that I've been using my entire career. And before you see, a lot of people today, in my experience, eliminate this part of the process and rely more on remote techniques, not actually dealing with visual looking at the rocks. And there are many things you can see by doing that. This particular rock was a good sandstone, very, very poorly consolidated sandstone, but it gives me the ability to talk about what we're trying to do here with visual rock characterization. So we in my experience, we have to use as many tools as possible to measure the reservoir properties, all at different scales. So we have the direct methods you're all aware of, is drilling and coring. And in the process of drilling and coring, it's a direct sampling of the rock formations. And out of that, we get cuttings and cores. Then we have our indirect methods, which are suites of logs and more sophisticated logs, so borehole imaging, NMRs, and so forth. And then the final indirect method would be seismic. So we're going to be dealing with the direct method of describing the rocks. We're looking at cuttings generally, sidewalls, as well as whole core. What can we do with these? Just as a reminder, we have log responses, and this happens to be from Baker Hughes's Atlas of Log Response, giving you a feeling for how the gamma ray, density, neutron, and sonic, and so forth respond to the different lithologies. We also have FIV SEM images. So here we have a nice little section of rock. What's in it? Here we see, let me bring up my laser pointer. So we've got pyrite. We have other minerals in this rock. More importantly, in this case, we've got kerogen, and pore space. So we have kerogen in green here. We have pore space in blue. And what visual rock characterization, what I'm calling visual rock characterization, really is we're trying to describe both the reservoir and the non-reservoir facies. Sandstones, limestones, dolomite, shales, siltstones, whatever. We need to be able to describe the texture, the structures, the diagenesis, the porosity. We can estimate mechanical properties using these techniques. There are several test methods that I use that help bring out these parameters. And I also talk about sources of error. So what is visual rock characterization? It's a systematic approach to describing drill cuttings and cores, and simply using a binocular microscope and reflected light. What we're doing is examining and identifying sedimentary rocks and minerals. And in our course, we actually have practical applications to reinforce these concepts. So what about mechanical properties? Well, we can estimate rock strength and competence, at least qualitatively. We can talk about the mineralogy. We can talk about the porosity. We can recognize diagenesis and cementation, textures. Mechanical properties also depend on layer thickness and the proportion of competent versus incompetent strata. We can identify frictional properties in the rock, and these mechanical properties then describe how a rock layer or multi-layer responds to natural and induced fracturing. So using these visual rock data, we can talk about the mechanical properties, but just as importantly, we can use these for facies mapping, tying in the framework of the rock and calibrating with wireline logs. We can talk about reservoir description, the nature and type and distribution of porosity. We can describe the diagenesis and how pervasive the diagenesis is within the rock. It allows us to give a quality assurance to wireline logs. So we can calibrate it to the rocks when we understand what the matrix and accessory minerals are. For instance, looking at pyrite or sylvite and how being able to recognize in the rocks, we can then go back to the wireline and understand better what we're looking at and give us an improved interpretation. Frequently, we can actually describe bypass pay. This has been used repeatedly over the last 100 years to identify bypass pay. Then the important thing about doing this is we're not trying to describe the rocks. People often describe the rocks, but what we want to do is extract all the information we can out of these rocks. So what do we use? Everybody knows these sorts of things in our equipment. we have now, this is standard binocular microscope with light source, a fluoroscope, examination trays, watch glasses, spot plate, grain size cards, water bottles, a hot plate, and pliers. And I talk about pliers because when we're looking at core, we don't want to destroy the whole core. We want to take a little chunk of the core. And that's what I use the pliers for. Glass rods, tweeters, metal probe, artist brush. So this is the list of equipment that I tend to use. And later I'll talk about clove oil and hydrochloric acid. So here's where we start, the whole process, whether we're looking at cuttings, at sidewalls, or whole core. As I said, we're doing this it's a systematic approach for drill cuttings and core description, just using binocular scope and reflected light. Several principles to think about is we need clean samples. And in the process, we have our clean samples. I always lay out 5 to 10 sequential samples so I can see changes, visual changes without the microscope. Important part of that is that these samples have some way to be labeled as you lay them out in your trays so that you don't get them confused in terms of the depth. Binocular microscope, I usually use a 10x magnification to get a wide view of the sample, and then if I want to do detailed examination, I will up that magnification. First thing you do is you scan the samples. What is the dominant lithology? In the case of cuttings, what's cavings? What we're looking for in each sample are new occurrences or significant increases in a particular rock type. Then we know we're changing our lithology, changing our rock type. If we're fortunate, and you can do this if you have a wireline log, is establish lithology breaks on the wireline logs and then use that to adjust the lag or the depth of your samples as compared to the log, because frequently samples are not labeled quite right on the sample bags because they haven't established the exact lag. And we can also look at the sample lag from sharp lithology changes such as dense beds, porosity breaks. So dense bed, you're drilling slower, porosity, you're drilling faster, or the occurrence of shales. So in terms of sample exams, like what I'm talking about, is we always need to know which sample you're working with. We always want to keep the samples in order, as I mentioned earlier. We want to put the samples back in the box in the correct order. As many of you know, there are millions of feet of cuttings from old cores that are available all over North America and internationally. So we want to put the samples back in the box in the correct order. That way the next guy comes along and they're in the right spot. If you're looking at core, you want to know the footage of the piece. But before you take it out of the box, make sure you know the orientation of the piece you're going to take out. So when you put it back in the box, it's in the right spot, in the right orientation. Be sure to put it back at the correct depth and in the correct orientation. And I mentioned a minute ago, test small pieces, break off a little chunk of the core, because we don't want to do a spot test with acid on a core face. It leaves lots of little dots. In other words, we want to save the samples for the next person who wants to look at the core. We extract our information, and there will be someone else who comes along and wants to look at those core cuttings at a later date. So first thing we need to do is to describe lithology. What are we talking about with respect to lithology? Obviously, we're looking for sandstones. We have siltstones, shale, limestone, dolomite, and chert. We might have anhydrite, whatever the dominant lithology is. For sandstones, the easiest thing to do, most of you have seen these textural diagrams of sand, silt, and clay, or sand, matrix, and gravel. It's very simple to describe these rocks as a shaly sand, a sandy siltstone, or siltstone, conglomeratic sandstone. Just a very simple classification, works quite well for this kind of work. So we've classified it as a sandstone. Well, here's a sandstone. These happen to be sandstone cuttings. So here's a specific cutting, but in this case, it's quite friable. So you see lots of other grains in here that have been separated, some of which might only have a couple of pieces associated with it. So it's a friable sandstone. And you can see some black shale in here. That happens to be cavings. So that was a relatively uncemented, a relatively porous sand. What happens if we see a sand that is cemented? In this particular case, it's a windblown sand. You can tell that from the rounding of the grains. And it also happens to be cemented with anhydrite. So all the white in between the grains in this case is anhydrite. Siltstones, they're usually quite nondescript. Dominant grains are silt. And sometimes they're quite hard. So they have some silicious cement, a lot of silicious cement in them, which is the case in this one. Shales, they're again, the big problem with shales is when you're in a thick shale section, it gets pretty boring to look at unless you look for what's different in each sample. In this case, it's micaceous, and there are actually a couple of fossils that you can pick out in this sample. So that's the sort of thing you're looking at. Well, let's look at carbonates then. So it's pretty straightforward. Look at sandstone, siltstones, and shales. What happens with carbonates? How do we recognize the carbonates? Well, the first thing we do is we can test it with a weak solution of hydrochloric acid. I always use a 10% solution of hydrochloric acid, and I drop put a drop of hydrochloric acid on a sample. And what happens? So we've dropped it on here. You can see it starts to fizz quite quickly. And that effervescence increases substantially with time. What happens with the dolomite? So here we have the same amount of time in between these, and you can see very little effervescence. You can see a lot of bubbles, individual bubbles in the dolomite. You're not going to see those in a limestone. What happens with time? It doesn't change significantly. Very slow effervescence. So that's how you could identify the difference between a limestone and a dolomite very easily. The other thing that's important is we want to be able to classify the limestones. This particular slide shows different classifications, starting, the Dunham classification. And all you geoscientists I know are aware of these. These are relatively simple, going from bound stone, wax stone, pack stone, grain stone, and so forth. Here I have a column called framework, and framework is the number of grains that are larger than silt size. So as that framework increases, we can correlate that back to our classifications. Folk would call this a micrite, which is with very few grains or few fossils in it. And a biomicrite as we begin to see some grains. Now, the other part about this is, here's Archie's classification, and his classification is based on how the grains are next to each other. How is the rock constructed, this limestone? So compact, it'll react one way with logs. If you have grain-to-grain contact, you call it sucrosic, a type 3. and a type 2 is chalky and microcrystalline to earthy. So Archie's classification relates to how we'd expect to see the wireline logs responding. This particular example here is a limestone core, and you can see it's composed of pellets and a lot of small fossils. In this case, here's another limestone. This one's an oolitic limestone. Here's a core piece of that oolitic limestone. Here's some cuttings of this oolitic limestone with a higher magnification, and you can see all the individual oolite grains in here. And of course, as the drill bit cuts through these, it breaks up the rock because there is some inherent porosity in here, and you begin to have individual oolites in the cutting sample. A dolomite. On the left, there's this is a dolomite. It has an anhydrite cement in it, and the black in here is actually bitumen, which is in the pores. In the process of changing from a limestone to a dolomite, you lose about 9% or so of the volume, so then you can generate some porosity. In cuttings, this is what this particular rock looks like, and you can see all individual dolomite rhombs in this one, along with a few pieces of cutting that are made up of these rhombs, but for the most part, the rhombs are loose in that particular sample. Anhydrite. What's anhydrite look like here? Well, this is a particular core, and you can see anhydrite beds within that core. Anhydrite is white generally and has some structures in it. Chert may be gray, it can be black, it can be white, it can be brown, but it's all pure silica. This happens to be a piece of the Monterey Formation. So we've talked about identifying the individual types of rocks. Now, within cuttings specifically, we need to be able to identify cavings and pore material. What are these cavings? They're lithologies from up the hole. These would be shales. They might be friable sandstones. It could be fractured beds. Well, if we've been logging the well, we've seen these lithologies before, so we know that they're cavings. How do they get there? Well, when circulation is stopped, the borehole is the cuttings will settle, and the first batch of cuttings after circulation has started again can be a very mixed bag. It also occurs when the borehole is disturbed during testing, coring, and tripping. It can be lost circulation material. If there's a dull bit, it's going to crush cuttings to a powder, and the cavings will be dominant. The dull bit also will cause drill string vibration. Cavings and pore material also occur because of low mud viscosities. So the samples aren't suspended properly in the borehole. And that leads to a mixing of finer material and coarse material in the cuttings. Faulty sample catching. I don't know how many of you before had to deal with this, but I've seen wells where, well, we're going to collect some samples, and who's ever catching the samples needs to catch up, so he puts a bunch of samples from the same depth into individual sample bags. Another thing that happens with faulty samples is the screens or the sieves are too large. And finally, it's not unusual if we're looking at clay stones and clay matrix or friable sand, that washes out if it's washed too hard, and that leaves only caving. So we need to be able to recognize cavings and pore material. Here's an example. This is an extreme example. Okay, here we have lost circulation material, walnut holes. Casing, pieces of the casing shoe. We have pipe shavings. They tend to be a little bit rusty in this sample. We have a lot of different lithologies as well, and it's almost impossible to understand what lithology is dominant and what lithology is coming from the bottom of the borehole with a sample like this. Another thing that you'll see is bit flour. Bit flour, particularly in limestones, happens in other types of rock as well. All it is compacted powder where the bit is cutting the rock into powder and it compacts it, and you get these chunks of bit flour. So we talked about lithologies, we talked about cavings and foreign material. What are the other things that we can recognize? Now that we've identified the rock, we need to be able to understand what's happened to the rock, and this is diagenesis. So this is metasomatism, dolomitization, recrystallization, fracturing, leaching, and pressure deformation. All of these things will affect the rock. What about dolomitization? The way I estimate the percentage of dolomitization, and on the left here we have a partially dolomitized limestone. On the right, this is pure dolomite, a nice porous dolomite. The one on the left, what I've done is etch the rock with, in this case, it was probably a cutting. I've etched it, and because of the differential erosion or solution by the hydrochloric acid, 10% hydrochloric acid, the dolomite does not dissolve as fast as the limestone. So all the dark in here is limestone, all the white are dolomite rhombs that stand above, and then I can use this to estimate the percentage of dolomitization. If I get a rock like the one on the right, I see all these beautiful, beautiful pores, make a wonderful reservoir rock. And everything in here is dolomite. Fracturing, how do I identify fracturing? It's pretty easy in a core. We can see nice filled fractures here. There's probably some, there's partially filled fracture there. It's very obvious, as I said, in a core. In cuttings, what you'll see is a piece, just break a piece off of that rock, and you'll see a nice flat edge with maybe some cement on it. The other thing that'll happen is you'll get some fracture fill pieces in your sample as well. So you'll see a nice piece of flat calcite that's flat on both sides. That is a fracture fill. Porosity. We need to be able to estimate porosity. And we have different types of porosity. So here on the left, in the upper left, we have intergranular porosity. This is a sandstone. It's porous in between the individual pieces of grains of sand. We have intergranular porosity in limestones as well. In the center here, we're looking at oolites with space in between the oolites that gives it porosity, and that space is not filled in this case. We've seen this sample already. It's intercrystalline porosity, beautiful intercrystalline porosity. We'll take another look at a couple of these in a minute. We have fenestral porosity. We have leaching and leaching porosity, as well as fracture porosity. So what do these look like in a little larger scale? Intergranular porosity here in the sandstone. You can see the pores and the individual grains of sand. There's also some clay in here, probably kaolinite. There's some cement that you need to describe. So, and these cements, as well as the clays, fill pores. So we need to be able to differentiate, and we can, between open pores and filled pores. And it's important to know what fills the pore, because that affects how it responds to logging, wireline logs. Intergranular porosity. Here's a good example of intergranular porosity in that limestone. Here's another piece of another nice pore that sits around this grain, and we're only looking at part of it. Intercrystalline porosity, porosity in between crystals, which is fairly typical of dolomites. What about fenestral porosity? This is fenestral because it's like a window. So within, and this particular sample is a microbialite, and as the carbonate was deposited, it's deposited in layers, and within these layers there were gas bubbles likely as methane was generated. These gas bubbles remained, the rock is lithified, and you have these pores that remain in the rock. Incidentally, the white in here, and I think I have a later picture of this, the white in this particular rock is anhydrite, filling some of the porosity. Leach porosity. Leach porosity is very important in limestones and dolomites, and it can be of different sizes. So I refer to very small pores. These small pores are less than silt size. We call these pinpoint porosity. We have larger pores in this rock, and we generally refer to them just as bugs. Well, this particular rock is obviously a dual porosity system. So we have, and that dual porosity system will react differently to the wireline logs. So if it's dominantly pinpoint, it's going to read high water saturations. If there's less pinpoint porosity, you'll have larger bugs, and the wireline logs will be reading hydrocarbons. So it's something to be able to understand. I know several fields that were discovered in terms of bypass pays because the dominant porosity was pinpoint porosity. So the wells were abandoned and later come in and re-drilled the area and came up with some nice hydrocarbon accumulations. Fracture porosity. Fractures can make up about 6% of the rock, up to about 6%. Fracture porosities can be open and they can be totally cemented. So I've talked about lithology, I've talked about changes in the rocks, and another change in the rock that's important is the cementation. So we have a porous rock. Well, these pores can be filled with voids, or the voids can be filled. These are precipitated after deposition, they fill the pore space. If you look and see crystals within the voids, they're usually larger and lighter in color than the host rock. Cementation can take a variety of minerals. It might be silica, calcite, dolomite, anhydrite and gypsum, kaolinite, siderite. I've seen sandstones totally cemented by pyrite, by halite, by anhydrite, as well as bitumen. You saw this one earlier. This is cemented with, totally cemented with anhydrite. With silica, what does silica look like? Well, if we look here on the left, you can see some very bright areas, such as where the arrows are pointing and where my pointer is at this point. Some more down here. That's reflections off of crystal faces. Well, what do they look? So it's pretty obvious in core, right? Well, let's look at cuttings. So here are some cuttings from a siliceous sandstone, and the individual grains, you'll get reflections off of the quartz overgrowth. So you can recognize that this has been silicified. In this case, it's not totally silicified. If you get to 30% silica cementation, it's going to look more like the one on the left. At 5–10%, it's going to look at cementation is going to look more like the sand on the right. Don't forget, all these black shale pieces in here are cavings. Another type is clay. In this case, we have a sandstone. It's actually has quite a bit of lithic material in it. We have quartz grains, chert grains, but within the pores, this white material, which is kaolinite in this case, clay. So this clay totally fills the pores. And so clay then becomes a cementing material. Anhydrite, you saw this picture earlier. As I said, these white blobs in here are anhydrite cement. So the rock properties we're looking for: color, texture, accessory minerals. With respect to porosity of those rocks, we're looking for porosity types. And in limestones or carbonates, you can have 3, 4 different porosity types. We need to be able to estimate the percentages of the porosity and then understand the relationship between porosity and permeability. As you know, the greater the porosity, the greater the permeability in general. We need to be able to describe the grain size. In clastics, we need to understand the rounding. How far is this particular grain traveled? How well sorted is the rock? What's the framework? I said earlier, that's the percentage of grains greater than 62 microns, which is silt size. So the rock properties, this is what we're looking for within the rocks to help us with our interpretation. Percentages, I've talked a lot about that. I spent quite a bit of time in my class about that. And we're looking at percentage of porosity. We're looking at percentage of framework, percentage of accessories. We're looking at the percentage of the degree of alteration. In other words, diagenesis, cementation, metasomatism. Often this is done through might be done through thin section, but as you know, who've been on wells before, point counting is accurate, but it's slow, and we need to be able to go through a whole series of samples without cutting thin sections. And at least as you improve and you get more experience, you can use the percentage charts, but with experience, you get quite accurate in terms of estimating the percentages. Accessory minerals, here's a couple of them. In this case, we have quartz can be an accessory. Glauconite is often an accessory. Glauconite is usually green or black. It's soft. You can see where, in this case, a probe has been pushed across the surface. Kaolinite, in this case, is plugging the pores. Halite is an accessory mineral. Dolomite is an accessory mineral. Siderite can be an accessory mineral. This is actually a siderite, but you also will find siderite as an accessory mineral within samples. Phosphates can be an accessory, and anhydrite can be an accessory. So we need to be able to identify these accessory minerals because these will affect our wireline logs. Fossils. Paleontology isn't worked that much, isn't taught that much or strongly in today's environment in at universities and colleges. But it's important to be able to recognize fossils because that kind of gives you a feel for deposition in terms of environment. In this case, we're looking at nice forams. At least you should be able to identify whether it's a foram, whether it's a crinoid, because they live in such a different environment. Finally, so we've described the rock. What's important? Why are we doing this? We want to look for oil stain. What does oil stain look like? I've seen a lot of people in my classes historically, they've never seen oil stain. So here we have on the left a couple of different samples in the tray. One tray is full of fluorescence because oil will fluoresce under long wave ultraviolet light. And the one on the left, somewhat is more spotty. So this stain will manifest itself in fluorescence, but you have to be able to identify, well, this piece of fluorescence is coming from a mineral grain. There are some fossils that will fluoresce as well, but we really want to focus on the oil stain and be able to differentiate between the two. So how do we do that? First of all, check it with ultraviolet light, and then we go to solvent. So if we see any brown stain that is not superficial, in other words, we can break the chip and we see the stain inside, it's probably oil stain. If we put the chip in a bit of water and it fails to break the surface from surface tension, it floats, It could be oil stain. If it's heated, you'll smell it. And particularly in a carbonate, if you're dissolving the carbonates, there'll be a residue left after etching, and that could be an oil stain. But you have to also remember that oil-based muds cause the chips to be completely oil coated. So what do? Here we've got cuttings placed in a watch glass, covered with solvent, and what do we see? We see a yellow or brown ring around it. That gets darker, and that's an oil cut. So it can be a light cut, it can be a medium dark cut. In this case, it's a medium cut. The next step is, well, let's look at it with a UV light and see what happens. So live oil begins to fluoresce, and you'll see channels of color coming out of the chip with fluorescence. This can be poor, fair, or good, depending on the intensity. A chip could fluoresce even if we don't get a cut, because if it's a very light hydrocarbon. The other thing to remember and how we identify crude oil is that crude oil generally fluoresces a yellow color, and refined oil fluoresces with a bluish color. So this is a good example of a crude oil, and it's in terms of color. It's not a refined oil, but that's how you can generally tell between crude oil and refined oils and oil-based muds. We can talk about, once we've done all this, we can talk about the environment of deposition. You know, you can describe if it's a marine environment, it's a fluvial environment. That's part of your description. You can then begin to understand the energy or the chemistry and the organisms that are affecting the deposition. And this information then can be transferred to log character. So you can then identify the log characters in terms of facies and use that for regional facies mapping. We can recognize unconformities. How do we recognize unconformities? Well, you usually see concentrations of minerals along the unconformity. It might be phosphate, it could be glauconite, could be manganese. We'll also can see abrupt changes in mineral assemblages. These mineral assemblages or fauna, the lithologic character, or even the cementing, these abrupt changes could mean unconformities. Iron oxide stains or manganese coatings along a boundary can recognize as unconformities. Often you'll see a basal conglomerate, and these conglomerates are quite heterogeneous, and they may be weathered. You might find weathered chert. You also can find porous zones in limestones that are caused by solution or groundwater, and these may be evidence of unconformities. I know in Utah, drilling into a karst zone, suddenly you've got these carbonates, and then you've got red siltstone or soil zones that pop up. Well, you've drilled into a former cave that's been collapsed and is filled with this red soil material. So visual rock characterization then, why do we do it? Well, we want to know the lithofacies, right? What's the depositional architecture? We can recognize these things in cuttings, in sidewall cores, and cores. Because not every well is cored, and other times we need to depend on getting information out of the cuttings. I know it's harder today with diamond bits, but it's still possible to do it. We want to be able to, not only the facies, but we want to be able to describe the reservoir and the non-reservoir rocks within a particular area. So here we're dealing with metrology, the mineralogy, the diagenesis, the changes that have occurred to the rock, the porosity, and what is the pore distribution? Are we dealing with dual porosity systems? We want to be able to, visual rock characterization allows us to calibrate the matrix and accessory minerals that we see in the rock with the lithology, the porosity, mechanical properties, and relate that back into our formation evaluation. We can also get an understanding of the reservoir compartmentalization and how how the uh, how the fluids will flow within the reservoir if we understand some of these other aspects, such as the pore distribution and the porosity. So visual rock characterization is not about describing the rock, because anyone can go in to describe the rock. Our role as geologists is extracting the information out of the rock so we can use it in our exploration, in our development, and even use it for, not only in oil and gas, but in hydrology as well. So we want to be able to extract the information. It's not about describing the rocks. We want to be able to use that information and extract it out of the rocks and relate that to our profession. Thank you very much. I think we're going to open up to questions now.
Yes, that's right. I want to remind our listeners that you can use the question feature in the GoToWebinar toolbox there, and you can type your questions in, and I will read them. You will be anonymous, and all of you who have attended today's webinar will later receive a link to a recording of the webinar. We'll send you an evaluation form, and you'll also get some information about how to schedule Dr. Merrill's class on visual rock characterization in-house at your company very soon. And let's talk a little bit about that, Bob. If one were to schedule a class, do you provide all the equipment? Do you have these microscopes and all the other ancillary equipment that you listed?
Well, it depends on where I am, actually, because I've done classes all over the world, and I do have microscopes available. And what I do is pair the participants up. So I have one microscope for two persons. So that can be, so that the two individuals can work back and forth and get a better build on each other's knowledge as they look at the samples. So I've got one microscope for two people. I've used, when we've done it in Houston, I use my microscopes. I've also shipped microscopes places, but that tends to get expensive after a bit. Internationally, I've met the classes that I've taught, the microscopes have generally come from the individual universities, or in some cases, companies have had sufficient number of microscopes to use. And depending upon where it is, and I will, when I'm doing it in Houston, I've got the materials that I showed you earlier. If I'm doing it internationally, I might take the materials with me, and they become part of the class as well.
And what about the rocks? Do you bring the cores or cuttings or samples, or does the client provide this?
So I've got a training set of rocks that I've carried all over the world. What I have found over the years is what's important to whoever is taking the class. They want to learn more about their rocks. So how do we find out about their rocks? Well, use their samples. So I've done classes with using the local samples of the company that I am working with, and it might be cores, it can be cuttings, it can be both. And as a little anecdote here, I once did a class in South Africa, and saw all of these beautiful sands in cores and cuttings. Well, and they were from. So then I decided I'd drive down to the coast south of Cape Town, and what did I find? I found beach sands looked just like the ones that I was looking at in the cores. So it would have been interesting to have taken taken the field trip before I looked at the cores. But the main thing is I like to work with the individual company material. I think it's much more acceptable. I do have some materials that I can use, particularly for cuttings descriptions. And I do have that set of samples that I bring for training materials.
Great. And is there any difference in how you would set up a class for unconventional reservoirs versus conventional reservoirs?
It's all the same. It's all looking at rock. Unconventional reservoirs, I would probably rely more on company material because, to be honest, I don't have that many examples of shale. Some people would say that all shales look alike. I know that I've looked at a lot of mud logs and lithology logs that show shale is above, shale is above, shale is above as you go down the log. And those sample logs, and no, shales do change. So depending upon where you are, they're going to be different. So I would prefer to use local samples and set the program up with that.
Okay. Could you discuss the need to be consistent in order of describing the samples by grain size, range, by cementing percent, cement mineralogy, mineralogy colors, fractures, such as the Worldwide Rock Catalog?
Sure. And so a long time ago, I worked for a company called American Stratigraphic Company. And that's where most of my techniques have developed out of. What I found there was you needed to have a consistent, or with a consistent framework, you can have different individuals describing the rocks very consistently and can begin to be able to compare the results from different individuals. And so what I have put together is a template that starts out with, and on that template I can record porosity types, porosity, lithology, grain size, rounding, sorting, framework, as well as add a description and then the degree of alteration of the rock, dolomitization, cementation, and so forth. So by having a consistent template, it forces you into putting together a picture of the rock, and you can go from well to well to well, or series of samples to series of samples, and know that in your descriptions that you've covered everything. It's important to be able to cover all the important aspects. And this template can change depending upon what the objective of your program is. But the consistency is critical.
You talked about using cuttings, sidewall cores. Do you ever do this type of work with outcrops?
You can do it with outcrops as well. The reason I focused on the cores is, or the subsurface material is, that's generally what we're dealing with. You can also bring in outcrops. You've got some outcrop samples. There are some differences because the exposure at the surface will have altered the rock. So then you've got to begin to understand how that surface alteration has affected the rock itself.
So certainly there are assets that have changed owners over the years, and some of these samples and cores may have been donated to core libraries. Or do you ever teach this class with the support of a public core library where you can get a variety of different rocks?
I've never done it in terms of public class, but I have done it with private classes where going to going to the core facility and having them lay out the core or lay out the material for us. So that is a good possibility. And as you know, in North America at least, almost every state now has a sample repository. That program was started in the 1990s.
And do you ever integrate this type of work with other testing, such as vitrinite reflectance, that sort of thing?
Well, all these other geochemical techniques are important. They're all part of it. In terms of the visual rock characterization, we can't see some of these things, but with the right, by expanding the template, yes, I've done a lot of source rock work over the years, and so I've been able to integrate that with my descriptions.
So do you believe most of this work is done on site with the well site geologists doing it with the daily cuttings, or is it done later by the geologists in the office?
Well, I'll give you my experience is that when I was sitting wells, I always ran my own samples and had the mud logger there as well. So the mud logger was washing and cleaning the samples, and I was doing my interpretation. The mud logger was doing their interpretation, because I had a vested interest in the results of that particular well, and I wanted to be sure that I was right. Mud loggers have a lot of other responsibilities. They do a good job, but they're not looking for necessarily the same things I am. So the other aspect, so that's on location. The other aspect of this is that I've done this work for years in my own office, because I want to be able to use it I want to be able to understand facies relationships, use it in my exploration programs, use it in my development programs. So that's all done in the office or within a sample repository. So you've got both parts of it. If you're in exploration, if you're doing exploration, you're not going to be spending as much time on location doing the work, except when you're involved with your own well.
So you mentioned that point counting is the most accurate approach. Can you talk about the mechanics of point counting for those who might not be familiar with it?
With point counting, you've got to take the time to make thin sections. So you put the rock on a glass slide, and then grind it down to where it's thin. So that takes time, and then you're sitting there with a petrographic microscope, looking at, let's say you're looking for pores. So every time your indicator is on a pore, you punch a button. Every time it's on a rock, you punch another button. So it's quite time consuming. It's possible to do. And if you're looking at thousands of feet of cuttings or cores, my experience is that I can get to an 80% solution pretty quickly without going to thin section.
Great, thanks very much. Why do you think oil companies rely on more indirect methods?
I think that they're easier. They're not time intensive. One of my mantras is the rocks don't lie. I've seen enough cases, and again, another anecdote was that I had a very experienced guy in my class, a mud logger in my class once, and he was very good at describing rocks. So in this particular case, I was giving a test at the end, And so I gave him a series of samples that had a sandstone that was cemented with siltite. So what did you see on the gamma ray? You saw a very hot gamma ray. It looked like a shale. And it took him a while to figure out what was going on. And yeah, some of the other logs had a strange response as well. But when you looked at the sample and understood that there was a sandstone cemented with siltite, you understood what you were looking at. So that's just an extreme example of why I like to look at the rocks and why I think it's important to look at the rocks. I think today companies tend to ignore that part because the other types of information, the indirect, the logs, the seismic data, all of this can be put together pretty quickly. It takes time to do the rock descriptions. And you have a lot of logs and actually sample logs sitting around in libraries that aren't used much anymore. It's all part, think of it in terms of just one part of the big data, which is the term that's talked about so much today is big data. Well, it's just another part of it. It all needs to be integrated. It all should be integrated. And in the process, the results will be better.
Well, Bob, thanks very much for your presentation today. It looks like we're at the end of our time, and we appreciate all of those who attended. As I said, you will get a link to a recording of this webinar and some more information about how to schedule Bob's class in-house at your location in the future. Thanks. Goodbye.
Thank you.
Bye.
Bye.